Network congestion begins with a simple physical limitation. It occurs the exact moment a router receives packets faster than it can transmit them out of a physical egress interface. Hardware has a built-in response to this bottleneck. When the exit interface is saturated, the router places the excess incoming packets into a temporary memory buffer known as a queue. This memory is finite. If the queue reaches 100% capacity, the router enters a state called tail drop. With nowhere left to store data, the hardware instantly discards all new incoming packets. When users experience lag or choppy audio, they often blame a lack of bandwidth. In reality, the origin of network latency and jitter is this specific hardware queuing mechanism. The packets are physically sitting motionless in a waiting line. To solve latency, enterprise networks must abandon these default routing behaviors. They implement quality of service, or QoS, a suite of technologies designed to mathematically manipulate these hardware buffers. By default, routers operate on a best effort model. This is a strictly first in, first out, or FIFO, queuing system. The router ignores the payload and simply processes whoever arrives first. In a single-file FIFO pipeline, a highly critical voice packet can get trapped behind massive background downloads. Latency is the physical time spent sitting motionless in this queue. Jitter is the variation in that delay, unpredictable wait times that destroy audio. Data traffic generates bursty and massive payloads. Voice over IP, by contrast, generates steady, predictable streams of micropackets. Data relies on TCP. It is immune to jitter, tolerates delay, and simply retransmits any dropped packets. Voice and video rely on UDP. It is a one-way protocol with no retransmission mechanism, making it highly vulnerable to packet loss. For voice traffic to remain intelligible, the technical thresholds are rigid. One-way delay must remain under 150 milliseconds, and jitter cannot exceed 30 milliseconds. UDP cannot recover from tail drop and cannot tolerate FIFO jitter. Without network intervention, real-time communications will inevitably fail during hardware congestion. To bypass FIFO logic, modern enterprise networks rely on a distributed architecture called the Differentiated Services, or DiffServ model. A router managing an active congestion event cannot waste CPU cycles performing deep packet inspection to figure out which traffic matters. The network clearly requires a pre-sorting mechanism. This all starts with the classification phase. Edge routers use access control lists or network-based application recognition to inspect and group incoming traffic the moment it enters the network. In the marking phase, the edge router injects a permanent priority value into the IPv4 packet header. The modern standard is the 6-bit DSCP field. Voice traffic is universally marked with the strict DSCP value of EF, or decimal 46. By permanently tagging the packets at the edge, the network shifts the computational burden of identification entirely away from its congested bottlenecks. When those marked packets eventually hit a congested egress interface, the router initiates congestion management. Instead of processing blindly, it reads the DSCP tags to determine the exact exit order. This logic tree demonstrates class-based weighted fair queuing, replacing FIFO with multiple parallel output lanes for different traffic classes. Within this sits low-latency queuing, a strict priority queue for voice traffic. The router must completely empty the LLQ first. By granting strict priority access, LLQ allows voice packets to entirely bypass the standard memory buffer wait time. This mathematical override eliminates hardware-induced jitter entirely. If the LLQ is constantly jumping to the front of the line, the remaining lower priority TCP data queues will inevitably begin to fill up. Congestion avoidance via WRED acts as a proactive monitoring system for lower priority queues. Before hitting 100% capacity, WRED intentionally drops select low priority packets. This triggers TCP's congestion mechanism, forcing the sender to slow down and preserve queue space. For strict traffic control, routers use policing to enforce a hard speed limit, instantly dropping any traffic that exceeds the configured rate. Shaping also enforces a speed limit, but instead of dropping excess traffic, it buffers the packets in memory to smooth out data spikes over time. WRED actively uses TCP's own logic against it. By sacrificing a few low-priority packets early, it saves the entire interface from locking up in a catastrophic tail drop. This split screen compares two saturated network links. The top relies on default hardware behaviors, resulting in blind collisions. The bottom manages the exact same data volume utilizing the complete DiffServ architecture. Throwing raw bandwidth at a network does not prevent the microbursts that cause jitter. Jitter is strictly a queue management problem. The DiffServ architecture succeeds by decoupling the heavy lifting. It handles traffic identification at the edge, reserving the bottleneck purely for execution. Quality of service steps in precisely when physical hardware reaches its limit, actively manipulating memory buffers to guarantee that a saturated link never results in the failure of mission-critical systems.